Hi, everybody. This is Dr. Nigro with a screencast for one of our notes portions in our unit on energy and work. All right, to start this notes packet, I asked my students to think about what they thought of when they heard the word energy. All right, so I want you to take just a second. I want you to think about that word, energy, and in your own words, list what you think of when you think of energy. All right, I'm going to give you just a second to jot that down. All right, and I'm not going to put an answer there. That's for you to come up with. All right, once you have that answer, I strongly suggest if you were not in class that you go watch the SciShow video entitled What is Energy? All right, this is easily accessible on YouTube. I also have added it to our Google Classroom under the Classworks tab. So I think it's a good overview of what energy is, and it's going to guide these next 5 questions. All right, so in that video, energy is described as the ability to do work. All right, now work is going to be an important concept for this unit. It's not what we think of in terms of a job. All right, we say that we are going to work. All right, but for a physicist, work is force applied over a distance. All right, now we're not going to worry about calculations for work yet. All right, that is coming. All right, but I just wanted you to know that it's not the same thing as, employment. All right. Further in that video, it talks a little about sources of energy, and one of those sources is chemical energy. And chemical energy is the energy found, or a better word might be stored, in chemical bonds. All right. The amount of energy within a chemical bond varies. It depends on what 2 atoms are connected by that chemical bond. It also depends on whether that bond is single, double, or triple. I mean, all of that comes into play when determining the amount of energy found within that chemical bond. Now, if we go even further and look instead of a molecule, we look at atoms, we find that one of the most powerful sources of energy is found within that atom, and that is nuclear energy. All right, it's the energy that can be harvested if we split the atoms in half or if we fuse 2 atoms together. All right, now throughout the universe, we have found that energy cannot be created or destroyed. And we've heard this before, this idea of not being able to create or destroy something. We talked about momentum not being created or destroyed. Right. Back in chemistry, we talked about mass not being created or destroyed. So we have the same sort of situation here. Energy is finite. It cannot be created or destroyed. It can only be transformed. All right. So we can change it from one type of energy to another, but we can't make any extra and we can't get rid of what we've got. All right. So that means that the universe contains a constant amount of energy and that we're just little pit stops for that energy on its journey. All right. Now, there are various types of energy. We've already talked about one, all right, nuclear energy, all right. In addition, we've got chemical energy, all right. But beyond those, we have other types of energy. We've got radiant energy, which is also sometimes called thermal energy. It's solar energy, energy that radiates from other bodies within the universe. The sun is an excellent source of radiant or thermal energy. All right. In addition, we have electromagnetic energy. All right. And this is energy similar to radiant or thermal, but it follows along a different wavelength than our radiant and thermal energy. All right. We also have electrical energy, and that's the energy of electrons in motion moving through a circuit and doing some work for us as they move. All right. And then finally, we have mechanical energy. And that, when you think of mechanical energy, you think of energy that's being produced because something is moving. All right. So a turbine or a dam where water is moving over a paddle wheel and it moves a turbine. That would be examples of mechanical energy. All right. Now, all of these energies can fall into 2 larger categories, which we should have heard of: kinetic energy and potential energy. All right. So kinetic energy is defined as the energy of motion. All right. So an object is moving, right? And that object is going to have a certain amount of energy that is associated with that motion. All right. So that amount of energy is equal to 1/2 of the mass of the object times its velocity squared. All right, so again, we're going to be using a mass value here, and we're going to be using a velocity value here. All right, now those two units for these, we're going to get kilograms times meters squared per second squared. They equal a unit that we used back in chemistry called the joule, which is represented by a capital J, and 1 joule is the same as a Newton times a meter. All right. All right, so whenever we see a joule now, we're going to know that that is a unit for some sort of energy. All right. Now, in addition to kinetic energy, we also have potential energy. All right. And this is energy that is stored.
I'm not sure I understand.
That is stored and is due to the identity or position of the matter that you are dealing with. All right, so we're going to be looking at these more specifically in class, but just as a heads up, all right, identity. So when we talk about potential energy due to identity, that's really getting back to this idea of chemical energy. All right, so what is that matter made of? What types of bonds are in that matter? All right, and how much energy can be stored within those bonds? All right, when we talk about energy due to position, we're talking more about mechanical energy. All right, and that for the most part is going to be gravitational potential energy or the energy related to springs. All right, we are going to focus on gravitational, but we should recognize that there are more than one type of potential energy. All right, so if it's a spring, we call that elastic potential energy. All right, if we're talking about the energy in bonds, that's chemical potential energy. And if we're talking about the energy due to its position above the Earth, that is gravitational energy. All right, these two are important, but not in physics. Well, that's not true, but not in our class. How about that? All right, we will deal with elastic potential energy in another unit if we get to it. What we are going to focus on instead is gravitational potential energy. All right, and that potential energy is equal to the mass of the object times gravity times the height of the object above the Earth. All right, now similar to what we saw for kinetic energy, our unit here is going to be the joule. All right, and 1 joule is still 1 Newton per meter. Okay? All right, so with these two formulas in mind, we're going to try a couple problems together. All right, then you'll be all set for the worksheets in the packet. All right, so let's start with some kinetic energy problems. All right, the current fastest car in the world is the SSC Tuatara. This car has a top speed of 360 miles per hour, which is 141.3 meters per second. If the Tuatara has a mass of 1,247 kilograms, what is its kinetic energy when moving at top speed? All right, so kinetic energy is equal to 1/2 mass times velocity squared. All right, so for this particular problem, that kinetic energy would be 1/2 times 1,247 kilograms times 141.3 meters per second squared. All right, so if we plug all that into our calculator, we find, oh, it's a big number. 1, 2, 4, 5, and then I have 4 zeros after that. All right, so that's 12,450,000 joules worth of energy that are being expended as that car moves at its top speed. All right, so for problem 2, a sloth, on the other hand, has been known to move at a top speed of 0.00044 meters per second. If the average sloth has a mass of 7.5 kilograms, what is its kinetic energy when moving at top speed? All right, so formula is the same. Kinetic energy is 1/2 mass times velocity squared. The difference here are our values. All right, so we'll have 1/2 times 7.5 kilograms times 0.00044 meters per second squared. All right, if we plug that into our calculator, we get a really, really small number, 7.26 times 10 to the negative 7th joules. So remember, when we get these negative exponents, that's a tiny number. So that's really the same as 0.00000726 joules. So that is a small amount, all right, which makes sense. It's going really slow and the mass is a lot less than that of our car. All right, so now let's look at problem number 3. A 1,200 kilogram car moves down the highway with kinetic energy of 350,000 joules. What is the velocity of the car? All right, so this one's a little bit different. So instead of finding kinetic energy, this time we're finding that velocity. All right, so our formula again is 1/2 mv squared is equal to kinetic energy. So we plug in what we have, 350,000 joules will be equal to 1/2 times 1,200 kilograms times that velocity value squared. All right, we're going to multiply both sides by 2 and then divide both sides by 1,200, and that's going to give us a v squared equal to around 583.3. We then take the square root of both sides, and we find that the velocity of this car as it moves down the highway is 24.2 meters per second. All right. The next question says, the car above applies the brakes, losing 200,000 joules of kinetic energy. What is the car's velocity now? All right, so the kinetic energy final is going to be equal to our initial amount, 350,000 joules, minus what we lost by braking, 200,000. All right, so we're going to now have a kinetic energy of 150,000 joules. So we're going to repeat our calculation above, but this time we're going to start with 150,000 joules. All right, we'll still have the half, and our mass is still 1,200 kilograms, and we'll be solving for v squared again. So we go through our math, multiply both sides by 2, divide by 1,200, and then take the square root, and we find that that braking has decreased our velocity to 15.8 meters per second. All right, so when the car lost kinetic energy, did it speed up or slow down? Since our velocity value is less, it slowed down. All right, what do you think would happen if instead of applying the brakes, you pressed on the gas pedal? So if we press on the gas pedal, I would assume that we would gain kinetic energy. And if we gain kinetic energy, I assume that that would allow us to speed up. All right, and what's really happening here is you're converting some of our potential energy that's found in those chemical bonds in the gasoline into mechanical energy, which the car then used to turn the rotors and then our wheels. Okay? All right, so those are some examples of kinetic energy. Now let's do one that's potential. All right, so for this example, Wile E. Coyote stands on a cliff that's 250 meters tall, holding a 50-kilogram anvil, waiting for the roadrunner to speed by. What is the gravitational potential energy of the anvil he is holding? All right, so remember, potential energy due to gravity is equal to mass times gravity times height. All right, so our potential energy here will be equal to 50 kilograms times 10 meters per second squared times 250 meters. All right, now we don't use a negative sign when we use gravity in our energy calculations because it's not, we're really trying to find what is the potential energy that's there. So we're not looking for a direction for our energy. All right, so if we do this multiplication, we should find that we have 125,000 joules worth of energy waiting to be used by that anvil. All right, as the anvil falls through the air, what is the potential energy transformed into? All right, so when the Wile E. Coyote's holding the anvil, it's not moving. And if it's not moving, then you can't have velocity. If you can't have velocity, you can't have kinetic energy. So at the top of the cliff, all of that potential energy is just that, potential. But if he drops the anvil, as it moves towards the earth at the bottom of the cliff, it's going to be speeding up, which means we're going to have velocity, which means that that potential energy is now being transferred into kinetic energy. What is the kinetic energy of the anvil just before it hits the ground? All right, so if we had 125,000 joules worth of energy at the top of the cliff, and we're not allowed to create or destroy energy, then I have to also have 125,000 joules worth of energy at the bottom of the cliff. All right, and if I know that, then I can determine the velocity of that amble just before it hits the ground. All right, and the just before part is important. It's kind of like when we were doing our ball toss work, where we always talked about right after we threw the ball and right before we caught it. It's the same idea here. All right, so kinetic energy is equal to 1/2 mass times velocity squared. So if we have 125,000 joules worth of kinetic energy, and I know that the mass of the amble is 50 kilograms, then I can calculate the velocity of the amble just before it hits the ground. So again, I'm going to multiply both sides by 2, divide both sides by 50 kilograms, and then take the square root, and I'll find that my amble, wow, it's moving pretty fast. It's 70.7 meters per second. Okay, so that's the notes portion for kinetic and potential energy and what energy is in general. All right, please come back and we'll do a second screencast that's going to look at the law of conservation of energy.